All right, you guys, we're going to pick back up with that third example on the slide where we were rewriting our expressions and then integrating. So here, I'm going to integrate 8 plus root x over 3x squared. But I want to go ahead and break up this expression first. The expressions in the numerator, 8 and root x, are both over 3x squared. So what that means is I can split them up to look like this. And then I can go ahead and do my rewriting. So I'm going to call this expression 8 over 3 times x to the negative 2. I'm just going to bring up that negative exponent. And then this expression here, you guys, I can call this x to the 1/2 over 3x squared. Now, a squared value, if you think about it, is just the same thing as a 4/2 value. So I can subtract these exponents and just have one x term. So what that's going to give me is plus 1/3 x, and if I have 1/2 minus 4/2, that's just going to be negative 3/2. So at this point, I'm all set to go to do the integration process. So what I can say is I'm taking the integral or antiderivative of 8/3 x to the negative 2 plus 1/3 x to the negative 3/2, and I'm doing that integration with respect to x. So I follow my process of simply adding 1 to the exponent and dividing by that same term. So if we look at the first operation, that means this x negative 2 exponent is going to go up and become a negative 1. And then that constant just comes along out in front. So I'm going to have x to the negative 1, and I'm dividing that by negative 1. Same thing with the negative 3/2. I've got negative 3/2, but I need to add 1. That's the same thing as saying negative 3/2 plus 2/2, which is the same thing as negative 1/2. So I have 1/3 times x to the negative 1/2, but then I'm dividing by negative 1/2. Because I just integrated, I need to bring along the c as well, the constant of integration. Now this setup here looks really yucky. I need to go ahead and make that look better. So I need to simplify square roots, simplify negative exponents, and handle those fractions that are going on here. So if I fix this term, I'm going to bring that negative out in front and call this negative 8. And I'm going to bring this negative 1 down below. So I'll call it 3x down here. Then this expression here, if I'm dividing by negative 1/2, that's really the same thing as multiplying by negative 2. So this is going to become minus 2 over 3. And then I've got x to the negative 1/2 down below. So I can just call that root x down here. Then I've got the plus c here. And that's my final answer for this operation. Now, when you want to confirm your answers, so if you've integrated and you want to go back forwards and take the derivative and make sure you have the right answer, you probably want to go ahead and stop at this setup to move forward with the derivative process, just so that way your exponents are already in the form that's easy to take derivatives. Okay, next up in your notes, you guys, we've got some antiderivatives or integrals for trig functions. So we have taken 6 key trig derivatives before. We've done sine, cosine, tangent, cotangent, secant, and cosecant. So we're just going backwards with that same series of identities. You've got this table over here, this blue table, and you also have the chalkboard in the front right side of the room that gives you that same information. So what we want to do is just analyze what trig identities do we have and how do we go backwards from them. So this asks us to find the antiderivatives of the equations we have below. So I'm going to go ahead and integrate this expression with respect to x. And again, I can really break this up into 2 times the integral of cosine x dx minus 3 times the integral of sine x dx. So if I take the integral of cosine, what I can just think that I'm doing is I'm going over to my cosine value in my table. If I integrate that, I end up at sine. And that makes sense because if I went backwards and took the derivative of sine, I would end up at cosine. So that means this operation is going to become 2 times the sine of x. Then if I go backwards, if I'm integrating sine, I'm going to end up with negative cosine. And the reason that I end up with a negative is that the derivative of cosine is negative sign. So if I start off with a positive sign, I must have started with a negative cosine in the derivative operation. So this is going to become minus 3 times this guy is going to be a negative cosine. And then I've got the plus c. So if we simplify those negatives, we're going to end up with 2 sine of x plus 3 cosine of x plus a constant as our original, oops, keep hitting the wrong button there, as our original function that we started out with. Again, if you work backwards, derivative of 2 sine of x, that's going to get you to 2 cosine of x. Derivative of 3 cosine of x, that's going to become negative 3 sine of x. So we know that we did that correctly. We can just repeat the process with some other trig functions. This one's even easier. We're just integrating cosecant squared and then cosecant and cotangent. So if I integrate cosecant, I can think of this as one separate integral first, cosecant squared of x dx. That's going to, when I go backwards, become negative cotangent of x. And again, the reason it's negative is because if you start with positive cotangent and take its derivative, you'd end up at negative cosecant. Then this piece, the integral of cosecant of x times cotangent of x dx, I just look and find that corresponding expression in my integral table, and that's going to be negative cosecant. So I'll end up with negative cotangent minus cosecant of x plus a constant. And I'm good to go there. And then I know if I were to work backwards here to take the derivative, cotangent would become negative cosecant. The negative makes it positive cosecant. Cosecant squared. And then negative cosecant would become positive cosecant cotangent because the regular derivative is the negative component. So that's our answer for these. So it's just matching. It's more or less table matching. And what you want to do is make sure that you have this process memorized. So just like we become comfortable with the 6 trig derivatives, we also want to know these 6 trig integrals, so the reversal of that process. The last topic area that we're going to get to today involves specific solutions or specific antiderivatives. So what this slide tells us is that all of the equations we found so far have represented general solutions. And that means that when you report your answer, you give the antiderivative and then you add the constant at the end, because we say, we don't know what this constant is, but the constant is just going to go away when you take the derivative. So what we want to be able to do is figure out what information do we need to identify a specific solution, so to identify what that C term would be. So as long as you have one initial piece of information about the function, you can go from having just a general solution, which has the plus c or constant of integration, to a specific solution. So if we take a look at these examples, it says find the specific antiderivatives given the provided initial condition. So I've got an antiderivative here, which means in order to find the original function, f of x, I just need to go ahead and integrate 3x to the 5th plus 2 with respect to x. So that's pretty easy. All I'm going to do is increment up the exponent here to a 6. So I'll have 3 and then x to the 6, and I'm going to divide by 6 as well. So I'll have 3/6x to the 6th plus the 2 will become 2x, and then I've got plus a constant. So here I can go ahead and simplify that to the 1/2 or to 0.5. X to the 6th plus 2x plus a constant. Then what I need to do is to use this initial condition to figure out what the constant's going to be. So all the initial condition says is, if you know one of the input values, then you can solve for the output value. So I know that if I am to plug 1 into the original function, I need to get out 10. So that means this is my x, this is my y, or my f of x. So let's plug 1 in. That's just going to become 0.5. 1 to the 6 is just 1, so 0.5 plus 2 plus some constant has to be equal to 10 as the output. So then I can say 2.5 plus a constant is equal to 10. So if I subtract over that 2.5, the constant must be 7.5. So then instead of saying plus a constant, my specific solution is going to be 0.5 x to the 6th plus 2x plus 7.5 is equal to f of x. So I can be more precise than just saying plus any constant, and I can say plus 7.5. So let's go ahead and try that once more. All we're doing here, you guys, is one step of integration and then one step of algebra, plugging in to solve for an unknown term. And it's always going to be a linear equation that you're solving here. So with this example, we want to go ahead and rewrite this function before we integrate. So if I bring it over here, I'll have the integral of 5. I'm going to rewrite that the fourth root of x as x to the 1/4. And then I've got minus x dx. So I'm going to be adding 1 to 1/4, which is the same thing as saying 1/4 plus 4/4. So I'm going to end up with 5/4 here as my exponent. So this will become 5 x to the 5/4 divided by 5/4 minus, there's really a 1 on this x, so this is going to be x squared if I go up by 1, divided by 2 plus a constant. And then I do want to make that look a little bit nicer. So when I do that, if I'm dividing by 5/4, that's the same thing as multiplying by 4/5, which means my 5's would cancel, and I'd be left with 4 x to the 5/4 minus, and then I've got a 1/2 or a 0.5 x squared plus a constant. So I'm saying that's my original function that I started out with. So at this point, what I would go ahead to check from this initial condition is if I plug in 32, I'm going to get out 3. So what's the constant that's missing in between there? So let's go ahead and plug in 32 for x. So we'll have 4 times 32 to the 5/4 minus 0.5 times 32 squared plus a constant. And our initial condition says that has to be equal to 3. So we might end up with some funky numbers here. But if we take 4 times 32 and raise it to the 5/4, you'll see that you get a decimal value. So kind of depending on the application, you would want to decide whether you need to keep this constant in exact form or if it's okay to round to decimals. We already did one example where we had a nice, clear, exact decimal. We're going to transition this skill into applied work. So I would go ahead and just get a decimal approximation in this case. So when I plug in this information and subtract off the 0.5 times 32 squared, I end up with negative 207.563 plus a constant is equal to 3. So then if I add over that 207, so I'm dividing this by negative 1, and then add that to 3, I end up with 210.563 as my constant, which means that the function that I started out with would have been 4x to the 5/4 minus 0.5x squared plus this 210.563. And so we're going to go ahead and do one full applied example, and we'll see why we might want to end up with those decimals or how they can be useful in that context.